multiplicative inverse, which is again a rational number. The sum of two rational numbers is rational. It satisfies the distributive laws. All of these things are true, including the ordering stuff is true for rational numbers. But what's not true for rational numbers is axiom 11, the least upper bound property. So this is the least upper bound property. It says that every non-empty subset of R that has an upper bound has a least upper bound. All right? Every non-empty subset of R that has an upper bound has a least upper bound. So like, to show you how this fails for rational numbers, you can make the following set. S equals 2, 1, 1.4, 1.41, 1.414, and so forth and so on, right? So what I'm doing is I'm taking truncated decimal expansions of the square root of 2. The square root of 2 is like 1.41 blah, 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 right? So that is an example of a set, right? What's the upper bound? Actually, what's the least upper bound for this set? What does it mean, least upper bound? Whoa. Yowzers. So what is an upper bound? An upper bound is a number which is above all the numbers in the set, right? So like, an upper bound for this would be 2. 2 is above all the numbers here, right? 1.5 would work, yeah?
So I think the least upper bound would be the square root of 2.
That's right. So you could prove that. The square root of 2 is the lub, the least upper bound of S. All right? The least upper bound of S is the square root of 2. And the square root of 2 is not a rational number. This can be proved. It's impossible to obtain the square root of 2 as a fraction of two integers. So that means that the rational numbers do not have the least upper bound property. In other words, the rational number system has holes in it. These holes are missing, so the rational numbers are not complete. The real numbers, on the other hand, have completeness. There's no holes in the real numbers. Where do we use this in calculus? Well, the place we use this in calculus is in what's called the, this room is always like crackling.
Why does it do that?
I don't know. There's like some problem with electronics. It's like shorting, or hope it doesn't kill my computer. But it does sound bad. So the intermediate value theorem. Do you remember what that says? What did the intermediate value theorem? Yeah.
Sorry, intermediate value theorem states that if A is less than B,
Mm-hmm.
and f of A is if f of A is less than f of B,
Mm-hmm.
then there exists a number between A that is equal to A plus A.
A plus B over 2. Oh,
Wait, sorry.
I mean,
F,
you got the right idea.
sorry, f
Mhm.
of A plus f of B.
Oh, yeah, but that's not the intermediate value theorem. That might be true. I mean, that's a specific instance of an intermediate value between A and B. It'd be the average of f of A and f of B. That is true. That's a value between f of A and f of B. The key is that if you have something like this, right? If this is n, and you have, let's say, f of A less than n less than f of B, or if you have f of B less than n less than f of A, which is not my picture, right? That makes n what's called an intermediate value. It's a value between f of A and f of B. And the intermediate value theorem says that if f is continuous, right? If f is continuous, then there exists some point in the domain of the function where n is attained, right? There exists a c between A and B, right? Like here. Right. Such that f of c is equal to n. Now there doesn't have to be just one. In fact, there could be many. But this is the intermediate value theorem. We most often use this in like root finding, right? If we have a function and it has one value negative, it has another value positive, right? Then we can be assured that somewhere between where it's negative and where it's positive, it goes through 0. What? Assuming the what? Assuming it's continuous, right? Okay, so let's look at the proof of the intermediate value theorem. That's something I did not do in class this semester, all right? Let's see here, what page did I put that thing on? And the proof relies heavily on the axiom, the completeness axiom. So it's around page 104 and 105 in these notes. We need to look. Sorry I spent so much time on the easy stuff that started class today, but you know, well, anyway. So there's the statement of the intermediate value theorem that we just talked about. Here's a silly picture of it, right? This one attains the value here, here, and here, you know? Hooray. So I have a few just these are homework problems that we had before, like stuff like this in your homework was there, yeah? And I talked about the root finding thing this semester as well. You remember? We did like divide and conquer. But this is what we should talk about. This is really the main reason I had you guys come to look at it today. I wanted to talk to you about these arguments. This is proposition 3.6.5. So let f be continuous at a constant, and let the f value of the function be non-zero. We can prove that close to the place where it's non-zero, it has to stay non-zero. That is a property of continuous functions that I find myself using in later classes often, whenever like analysis is involved. So if, let's see here, so what this is saying is if f of c is not equal to 0, then I can either keep f of x positive or I can keep f of x negative for all values within plus or minus delta of the place where it's non-zero. The proof goes like this. Assume that it's positive. Let epsilon be f of a over 2. Right? That's also positive. Because the limit's given to exist, we can choose a delta such that when we're within delta units of c, we're within f of a over 2 units of f of a, f of x, you know, like that. But then that, when we unwrap the inequality, we have this, right? And then if I add f of a across this, it gives me 0 less than f of a over 2 less than f of x less than 3af over 2. What's that tell me? That tells me f of x is positive. Yay. So that's what I wanted. F of a positive keeps f of x positive for x close to a. If f of x is negative, f of a is negative rather, I can then, why do I put a minus here? Wouldn't that make it negative? Doesn't epsilon have to be positive? Why can't I put a minus here?
Because f of a have to be negative.
Right, because f of a is negative, right? So f of a is negative, which makes this positive, despite appearances. And I think this is one of the fundamental confusions of introductory students is that minus necessarily means negative. It doesn't. Okay, so anyway, delta, choose it so that we're within minus f of a or 2 units, unwrap the inequality, add f of a across of it, and you get f of x is less than f of a over 2, which is negative, which shows you that f of x stays negative within plus or minus delta of the point. So this is how we prove. We prove with epsilon deltas is the point, the larger point, all right? Now this doesn't yet have anything to do with the completeness of the real numbers, right? This is just a simple lemma that I really should test calculus on every semester, honestly. But the truth of the matter is, if I forced this issue with calculus 1 as the students are currently coming to me, it would be very bad because they're not ready for this kind of question, unfortunately. But you guys are. So that might be a question on your final to prove that proposition. All right, so but I'm going to try to make up another homework set, Jacob, that's focused on these kinds of things, just to give you a chance to kind of like finish your thinking about it, okay? Because we don't, your final doesn't have to happen like right this instant, right? We can take another week and let you sort through some of these things, right? And by the way, if you don't end up not understanding them, it's not the end of the world. I just want to give you a chance to try, okay?
Yeah.
So this is Bolzano's theorem. Bolzano was a monk, and I think he was a monk, I don't know. But this theorem's pretty awesome. It is the sort of prototype. It's the prototype of the intermediate value theorem. It's actually what we tend to use. See what the theorem says. It says, let f be continuous on a closed interval a to b. That was supposed to be a comma. It became a, I don't know what happened there. This is supposed to be a comma b. All right, such that, check this out, f of a, f of b less than 0. What's that mean? If the,
Either f of a or f of b is negative.
and the other one has to be positive, right? So it's either plus minus or minus plus. So that's a nice way of saying that 0 is between f of a and f of b. 0 is an intermediate value for the function, is what this means. Then there exists c such that f of c equals to 0. All right. So here's the proof. Suppose f of a is less than f of b, then that, all right, imply. So I'm going to look at the specific instance that f of a is less than 0 and f of b is greater than 0, right? Because if I can prove it in that case, we should be fine. We can easily adapt the proof to the other case once we do that case, right? So we can use axiom 11 to the heart of the proof. The goal is to find a non-empty subset which has an upper bound, all right? So axiom A11 then provides the existence of the least upper bound, and we want to construct a set which has the property desired in the theorem, all right? So here's what we're going to do. We're going to find S to be the set of X in AB such that f of X is less than 0, right? So we want 0 to be the least upper bound of this set. Make sense? Maybe? All right, so notice that, first of all, is it a so one of the things about axiom 11, if you go back and read it carefully, it says every non-empty set which has an upper bound has a least upper bound. So the set has to be non-empty. To prove something's non-empty is a simple matter. You just have to find one thing. So in this set, A is in this set. See, because f of a is given to be less than 0, therefore A meets the criteria of S, as such A is in the set. So that's great. So S is non-empty. And it's also clear that it's bounded. See, because B is a bound. Every X is in the interval A to B, which means B is an upper bound for the set. So it's bounded above. Non-empty, bounded above. Therefore, it has to have a least upper bound according to axiom 11 of the real number system. And so to say C is the least upper bound means that any other upper bound of C is larger than C, right? So now we just break into cases. We look at the cases. The argument's really not that complicated, but it does require case-wise logic and a little bit of patience. So let's just keep at it. Let me scroll down a bit. All right. So we want to show that f of c has to be 0, for c being the least upper bound, all right, of that set S. Now, if f of c is less than 0, so the continuous function f has f of c not equal to 0. But what does that mean? By the proposition that you're going to prove on your final, right? No? You said you wanted to prove the proposition 3.65? You don't really want to? Oh, okay. But you'll consider it. So by proposition 3.65, there exists a delta greater than 0 such that when x is between plus or minus delta, and in the interval AB, f of x is less than 0. But what's that mean? That means that there's some x between c and c plus delta, which has f of x larger than c. But that's a problem, because c was supposed to be the upper bound, but you've got f of x is bigger than f of c, right? So x is an s and it's larger than the upper bound c. Therefore, c is not an upper bound. That is a contradiction. Therefore, we cannot have f of c being negative. So basically we're using that proposition 3.65 paired with, the definitions here. How about f of c positive? F of c is positive, then f of c is not equal to 0. So by proposition 3.65, there exists a delta such that the values of f of x are positive near c. So that means that any x in here has f of x greater than 0, right? Which means that f of x, let's see here, what's that mean? We have f of x is greater than 0 and x is not an element of S, which means that x is equal to c minus delta over 2 less than c is an upper bound of S, which is smaller than the least upper bound. Again, c is not the least upper bound of S, so this is a contradiction. Again, we cannot have f of c greater than 0. So if we think about f of c being less than 0, if we think about f of c being positive greater than 0, and we reason through the logic given to us by proposition 3.65, in both cases we come to a contradiction, and we're forced to conclude that no, f of c must be 0. Which is to say that the intermediate value exists, right, to reach 0. This is Bolzano's theorem. So like intermediate value theorem with n equals to 0 is Bolzano's theorem, basically. And then to prove the intermediate value theorem, it's easy. Like you just, basically it's a corollary to the Bolzano's theorem. Here it is. So let, n be the intermediate value, that let g of x be f of x minus n. So if f of x is continuous, then g of x is continuous, right? So f of a less than f of b means that n is an intermediate value, which then means that if we subtract n across that inequality, 0 is an intermediate value of g of x, right? G of a and g of b are above and below 0, other way around. So if we apply Bolzano's theorem to g, we get c such that g of c is equal to 0, but that means that g of c, which is f of c minus n, is equal to 0, which is to say that f of c is equal to n. So, yay! And the proof of the other direction is similar. So basically, we use a careful argument based on the completeness axiom of the real numbers to prove the intermediate value theorem, to prove the Bolzano's theorem, and then we adapt that for the to get the actual intermediate value theorem. Now the other theorem that I didn't prove in Calculus 1, which is somewhat technical, and I don't even have in these notes, is the extreme value theorem. But I'll have to talk to you guys about that in some other course. It's like a little bit beyond Calc 1. So sorry about that. But anyway, I just wanted to show you guys this because it is something I have classically covered in Calculus 1, but I've gotten out of the habit of covering it lately because like students are, a little bit less prepared coming into it. So I'm trying to spend more time on like, pre-calculus kind of stuff in the course, and I don't get quite as far in the analysis anymore. So anyway.
Was he like some sort of math monk?
I think he might have been like a Jesuit priest or something. So yeah, I mean like some of these monks, they had, like scholastic interests. Like, wasn't the guy who like breeded the beans and stuff, wasn't he like a monk too?
I think
like
he
the
was. Mendel?
Yeah, the Mendel. Like all these guys did stuff. They had time on their hands and food to eat, so you can think. Anyway, that's probably it for this summer. I think I'm just going to give you guys some homework problems that are kind of based on the ideas we talked about today, just to try to, settle these things. But it shouldn't be much. It probably shouldn't take you more than like an hour or two to work them out. So, all right. And I'm also going to try to give you like a couple of more difficult epsilon delta proofs because I think that would be interesting and help you kind of finish that thought. So, yeah, that's it.